Record.
I know, I messed it up on the Zoom.
I just wanted to
We're
make
gonna go
sure.
through them all.
I was so confused. I was
Yeah,
like,
no,
what?
that was my fault. I don't know what I was doing, but yeah. Okay. So yeah, so I know on the recording, like I somehow did one problem in another problem spot, and I don't know. So we're just gonna do them. I don't know what I was doing. So we will do them all today, so don't worry. You need your best friend. You need your eye clicker. You will absolutely need your best friend today. And the calculator. Yes, ma'am. How many carbon products are there? So it has to have 4 different things. 4 different. So this is the carbon. This is the carbon. This is power carbon. No, this power carbon. 1, 2, 3, 4. Yes. This 1, 2, 3, 4. This 1, 2, 3. 4 different. No, right? Right. Only 1, 2, 3. So that's not one. This one. So 4 different. 1, 2, 3, 4. Look.
I use the cross that it every time it has a
But you gotta
cross. Okay.
You gotta look.
Okay. Thank you.
Yep. Okay. All right, y'all ready for eye clicker? Any questions on the exam? Okay, just make sure it goes in the basket before you walk out the door. Make sure it goes in the basket before you walk out the door. What did the pig say that got stuck outside? I'm bacon. My son really liked that one. He really, really, really likes bacon. Okay, so here we go. Tell me, what is it called when a mixture has evenly dispersed substances? What kind of a mixture is it? We have 1 minute. And you can have your notes out. There's nothing wrong with having notes out. Okay. Turn and talk to the people around you and click in again. I think that didn't take y'all very long. So we'll say 30 seconds. 30 seconds. Make sure you click in again so you get all your points. And if you're on Zoom, you can chat on Zoom. Okay. So what did we say? Okay. So evenly dispersed is homogeneous, right? Diluted and pure have nothing to do with how evenly dispersed the substance is. It's either homogeneous or heterogeneous. Even is homogeneous, non-uniform is heterogeneous. Okay, now we have a cup of coffee. It's got some sugar in it. It is a homogeneous mixture, and we call that kind of a mixture in particular a blank. One minute. Definitely have time to check your notes, right? Ten seconds. Don't leave it blank. Okay, turn and talk. Click in again. Should be 30 seconds. 30 seconds. Some good ways to build up your eye clicker points, right? You got this. Okay, 5 seconds. Make sure you've clicked in again. Okay, so what did we say? Sugar is a solution. How did you know it was a solution? What's the difference? So you shouldn't have picked solvent and you shouldn't have picked solute because those together, right, make the mixture. So it was between colloid and solution. How did you know it was a solution and not a colloid? It should be clear, right? Transparent. So why is a solution clear and a colloid not? A colloid has small proteins, fats. What's important about those proteins and fats? They're not what? They're not soluble, right? They're in suspension. They are there and they're evenly distributed, but they don't settle, right? So if you put cream into milk, and if cream into milk, haha. If you put milk into your coffee, You can walk away from it after having stirred it, right? You can walk away from it. And do you come back and you have a layer of coffee and a layer of milk? No, it's still mixed, right? So when you do that, you have a colloid. It's uniform, but it's still a colloid. But if I put sugar, what does sugar do? Sugar dissolves, so that makes a solution, because when it dissolves, it becomes clear or transparent. All right, let's see how well you can apply that. Oh, and we did that in class, so we're not going to do that today. So which of these is a colloid? Which of these is a colloid? Okay. Turn and talk to the people around you.
Yeah, that's what I'm thinking.
So click in again. 45 seconds.
I didn't see if it says that those solutions that are homogeneous textures and it's chunky and thick. It's not more. There's no fruit, like a fruit texture and a fruit around it. It's not homogeneous. So that's not the easy for the cloud construction. It doesn't say here.
Okay, 5 seconds. Click in again. Make sure you click in again. And we have a little debate going on. I like it. I like it. All right. So what did we say? Let's see. Question 5. Oh, we're very mixed. Okay, so let's talk about this. What is ampicillin? A liquid that must be shaken before use. Shaken before use. Tell me about that. It settles. So what kind of a? It's a suspension. So if it's a suspension, it can't be a colloid, right? Okay, Pedialyte, a clear liquid. It's a solution. So anything where you see clear liquid must be a solution. Where else do you see clear liquid? In E. So it can't be, this is another solution. Can't be E. Okay, a fruit and yogurt smoothie, a chunky, thick, turbid liquid. If something is a colloid, what kind of a mixture is it? Homogeneous or heterogeneous? Homogeneous. If it's chunky, is it homogeneous? No, this is heterogeneous, right? And if I walk away from it and I have chunks of fruit, what's going to happen to my chunks of fruit? They're going to settle down. So what is this? Lemonade, a cloudy liquid. What is this? Colloid. Can't even see. So what tripped you up on that? So yeah, we're 6. So it should have been D. Like we had 11% that said, right? We actually went down. This is, I think, the first time ever we went down. So what happened? Do you understand the difference now? Yeah? Yeah? Okay, one more clicker time. Which of these is a colloid? Trying to help you out here. Which of these is a colloid? Trying to help you out here. It's saying not going. All right, try again. I might have to go in and mess with it when we get out of class. 30 seconds. Which of these is a colloid? It's not supposed to hurt you that much. So when you talk about a colloid, it's going to be cloudy. Colloid's cloudy. So kind of think about that. Colloid is cloudy, but it's uniform. It's completely uniform in composition. So make sure you've clicked in. Okay. All right. I think I got one more for y'all. This one, I am going to give you 3 minutes. So select the correct products for the balanced chemical equation for the hydration of Na3PO4. Do not look at the answer choices yet. Get out a sheet of paper, take out your pen, write the reaction, then compare your answers to the answer choices. I will give you a full 3 minutes to do this. Don't look at the answer choices. Remember, you have 3 minutes, so you don't have to rush. Please make sure those masks are covering noses and mouths. So we're coming up on 2 minutes, 10 seconds. So we'll go all the way to 3 minutes. Okay, 15 seconds. Make sure you don't leave it blank. 5 seconds, no blanks. No blanks. All right, turn and talk to the people around you and click in again. Well, you're getting pretty confident in your answers. Not a whole lot of debate. Give y'all 30 seconds. It looks like everybody's pretty happy with their answers. Okay, so I'm going to do the same thing that I said for y'all to do. Na3PO4. When I do this, how do I write this? I kind of want to move it over, but that's okay. Oh, I can't. So how do I hydrate this? I add water, right? So I'm going to assume this is a solid, unless otherwise told. So what does this disassociate into? I have a metal, which is Na, and then I have a polyatomic ion. Do I ever split up my polyatomic ion? No, indeed not, right? Okay. So I have Na, and this is going to be aqueous because we put it in water, plus PO4, and it's aqueous, but I'm missing two things. What two things? Charges, and check that I am balanced. So what's my charge on Na? +1, I got that from the periodic table. What's my charge on PO4? 3 minus, and you could have done the reverse crossover, or you could just go look them up. Either way is fine. Am I balanced? Nope. What is not balanced? The sodium. So I needed to put a 3 to make it balanced. So what should my answer have been? Should have been B. So what did y'all say? Excited. Let's see. Oh, that's awesome. That's awesome. Okay, so very good, very good. So remember, we do not break up a polyatomic ion. Never break up. They're together. Y'all let them be. Don't break them up. Right? They'll rock the boat. Okay. Go to your in-class problems. And I know I got kind of crazy when I was doing this. I don't know what I was doing. View full screen, one problem in another place, or I don't know. So we're just gonna do these, all of these. What is the concentration in millimoles per liter? So the rest of this section is all about calculating concentration. And there are different ways to calculate concentrations. You could do it in molarity, right? What is molarity? Now, as I say this, go and get your best friend. You see down here on my best friend, I have this whole big section that says solution equations. What's this chapter on? Solutions. So most of what you need is going to be right here. So what is molarity? Moles of the solute over liters of solution. And so sometimes we say this as the big M, right? So there could be variations on molarity, like in the first problem, we're asked for concentration, not in moles per liter, but in millimoles, right? So you have to be careful about that you recognize the milli. Milli always means 1/1000, right? We're also going to be looking at concentration in terms of percents. So we'll talk about that. We're looking at concentration in terms of parts per million, parts per billion, right? These are all different ways to look at concentration. So we're going to start with molarity, and then we'll move on to all the others. So one thing I want to tell y'all, what is the equivalent that I would use in problem 8.23? I'm asked, what is the concentration in millimoles per liter of a Ca2 plus solution that is 2.50 milli equivalents per liter? Remember, equivalence is equivalent charge. So I could say in 1 mole of Ca2 plus, I have what? 2 equivalent charges of Ca2 plus. Y'all agree with that? Now, I'm going to show you a little trick. If this statement is true, then this statement is also true. In 1 millimole, 1/1000, right, of Ca2 plus, I have 2 what? Milli equivalents of Ca2 plus. You don't have to automatically know that. But if you don't automatically know that, you're going to be converting out of milli and then right back into milli. And so it's going to be work you don't need to do. But it's okay if you do, because you get to the same answer. Okay. So I'm going to use the equivalents that I have. So what do I start with? 2.50 milli equivalents per liter. Now I could get rid of milli equivalents, convert to moles, convert from moles to millimoles, but that's a lot of steps. So I'm just going to use what I know, and I'm going to say I have 2 milli equivalents Ca2 plus per 1 millimole of Ca2 plus. So what do I have? .5 divided by 2, you should get 1.25 millimoles. And you could do milli, no, not for this one. Yes, you can. Millimolar. You could do that, or you could say 1.25 millimoles per liter Ca2 plus. It's the same thing, right? Because the big M, what does the big M mean? It means moles per liter, the big M. The big M is the same thing as moles per liter. Right? Doesn't matter. Okay. So what is the concentration in milli equivalents per liter of an Mg2 plus solution that is 100 millimole per liter? So in this one, I'm starting with something that is 100 millimoles per liter, and I want to get to milli equivalents per liter. So can I just kind of stay in the milli? Yeah, right? Okay, so what do I know? What's my relationship that I know? If I want to get rid of millimoles and I'm going to introduce milli equivalents, what do I do? So because this is Mg2 plus, because I have 2 charges for every mole, I'm going to say I have 2 milli equivalents per millimole, milli equivalents per millimole. So what do I get? I want milli equivalents per liter, and that's what I have. So what do you get? 100 times 2 is 200 milli equivalents per liter Mg2 plus. Okay. Next one, what is the molarity? So what unit am I going to try to get to if I want to know molarity? Moles per liter. Do you have to memorize that? No, it's on your best friend. So if you forget, don't freak out. Just go look at your best friend. Okay. So what is the molarity of a 250 milliliter solution containing 4.2 moles of ZnCl2? I know my goal is to get to moles per liter. What do I start with? It actually doesn't matter. Doesn't matter at all. So which one do you want to start with? We could start with the 250 milliliters or the 4.2 moles. What do you want to do? For 4.20 moles ZnCl2. Now, that's how many moles I have per what? 250 milliliters. Whoa. So what do I actually have to change here? Do I need to change my moles? I just need to change to liters, right? Okay, so I put milliliters on top, I put liters on bottom. I know I have 1,000 milliliters in 1 liter. What do I do? What do I get? Excuse me. My milliliters cancel, I'm in moles per liter. What do you get? 16.8. My units are moles per liter, or what else could I say? Big M, right? 16.8 big M ZnCl2. Okay. What is the molarity of a 750 milliliter solution containing 210 moles of Na2SO4? It's the same thing, right? We do exactly the same thing. We take 2.10 moles, we divide it by 750 milliliters. We're trying to get to molarity. So all we got to do is get rid of milliliters and introduce liters. Our milliliters cancel. We're left in moles per liter. And what do you get? .8 moles per liter, or 2.8 molar Na2SO4. Okay, so I think I did 8.27 in the video, right? Yeah. Okay. All right. Now, what is the potassium ion molarity of 850 milliliters of blood plasma containing 10 millimoles of K+? So what do I start out with? 10, what does the dot mean? 2 sig figs. So my answer should be 2 sig figs. Millimoles K+, 850 milliliters. And I want to go to potassium ion molarity, which is moles per liter. Now, you want to do this the long way or the short way? I like the short way, right? So I'm going to show you the long way so that the short way makes sense. I'm in millimoles per milliliter, right? So I got to get rid of milli in the moles and I got to get rid of milli in the liters. So let's convert millimoles first. I have 1,000 millimoles in 1 mole. Okay, so that means my millimoles cancels, I'm in moles. Then I know I have 1,000 milliliters in 1 liter. So my milliliters cancel and I'm in moles per liter, which is what I want. But what did I just do? I divided by 1,000 and I multiplied by 1,000. Did I do anything? Nope, I didn't. Why? Because if you have millimole per milliliter, if I cancel the mole, the milli, excuse me, all I end up with is moles per liter. It's the same thing. So like if you have milligrams per milliliter, it's the same thing as grams per liter, right? Because the millis just cancel. So you could recognize it or you could go through it. It does not matter. It does not matter at all. So what do you get for 8.28? So I got, yep, 0.0, what was that? 12 molar K+. Okay. All right, now, sometimes you're going to be in a situation where you actually have to measure out some amount of something to make a solution of something for your patient, right? It's going to happen. It's going to happen often. So kind of the rest of this section is being able to do that with different kinds of solutions. So this one, we want to know a solid, right? How many grams of NaCl must be added to water to create a 2-liter solution of a 0.154 molar normal saline solution. So what's my goal? Grams of NaCl is my goal. Not gal, goal. All right. Okay. So what am I going to start with? 2 liters or 0.154 molar normal? Doesn't actually matter. Doesn't matter. Which one do you want to start with? Let's pick the 1.54. What does the big M mean? Moles per liter of solution. But was I told that I was going to make a liter of solution? No, how much am I making? 2 liters. So what I'm going to do is I'm going to multiply by 2 liters, and I'm going to lose that liters, right? And I'm not going to introduce anything at the bottom. Do I need to introduce something at the bottom? No, because I'm trying to get to just plain old grams. So I really do need to cancel out that liters. Some people like starting with the 2 liters first and then saying, okay, I know for every 1 liter, I have 0.154 moles, but it's the same thing. It's the same exact thing. Yeah. Some people just don't like to have one in the middle without something underneath. It's okay. It's cool. Either way works. Okay. So now what? I'm in moles, but do I want to be in moles? No, I got to get rid of moles, and I'm going to introduce what? Grams. Can I convert grams to moles? You can. I know you can. It's not given in the problem. Where do I need to go? Periodic table to get the molar mass. So molar mass of NaCl. How do I do that? I add them up. So I look at sodium. I have 1 sodium atom. And what's the mass of a sodium atom? 22.99, right? Plus my chlorine, I have 1, and that chlorine is 35.45, right? So what do you get? 58, ooh, 58.44 grams per mole. So then I just go and plug that in, 58.44 grams per 1 mole. So now my moles will cancel and I'm left in grams. So what do you get? $18. Now, y'all know, y'all laugh at me that calculator clicking is my favorite sound on the planet, but the more you do it here in class, the easier your homework and the exam is going to be, right? So make sure that you're doing it so that you're getting the same answer that I'm getting. Because if you're not, you can raise your hand in the middle of class and go, wait, I didn't get that. And I can help you, okay? All right. So the next way that we can calculate concentration is through percentages, right? So if I'm going to do a percentage, there are a couple of different ways that I can do it. So take out your best friend and look at your best friend. And do you see under concentration solutions, you have the very first one is percent concentration, which is just parts of your solute over 100 parts of solution. We're not going to use that too much, but look at the following ones. Now we have percent mass by volume. So whenever you're doing mass by volume, you're taking some number of grams of a solute and you are putting it into some milliliters of solution, right? And then because we want it to be a percent, we're going to multiply times 100. So what you're going to see for all the percent, whether it's mass by volume, the next one's mass by mass, the next one's volume by volume, we're always multiplying times 100. So whenever you multiply times 100, you're getting something that is called a parts per 100. Parts per 100, right? So that's why we multiply, when you multiply times 100%, right? That gives you parts per 100. So look down below percent volume by volume. What's the next equation? Parts per ppm, parts per million. Why is it called ppm? Why is it called million? Because you multiply not by 100, but by a million. ppb, what is that? Parts per billion. So you use these parts per million and parts per billion for things that have really small concentrations, really small, okay? But for everything else, we're really using parts per 100, which is what we call in everyday life percent. Okay, so calculate the mass percent by volume. So if I want my percent mass by volume, what's my formula? Grams solute over milliliters solution times 100. Okay, so A, we have 75 grams of our solute, which is Na2SO4, divided by 250 milliliters of our solution times 100. So what do you get? I got a 30%. Did y'all get 30%? And this is 30%. Do we just leave it like that, percent? We have to specify. We have to specify what kind of a percent that is. So that is a mass by volume percent of Na2SO4. Okay. So B, how much sugar is in a carbonated drink? Oh, that's gross, right? To really think about that. All right, so we have our grams of our solute, which is 39 grams sucrose, over 355 milliliters of our drink. Our drink is the solution. So what do we get? Oh, times 100. Don't forget to times 100. 11%. So when you drink a non-diet soda, 11% of what you are consuming is sugar. Yeah. All right, let's see. So we did 8.33 in the video. All right, here we go. So here's another concentration, and it is in percent, but it's in percent of mass by mass. So be super careful of this. When we're saying percent mass by mass, we're saying grams of solute, right, over grams of solution. What is the solution? It's solute plus solvent. In all the previous problems, it already combined it for us. But here we have to do it. I'm telling you, more people get this one wrong than any other concentration problem. So I'm telling you now so you don't get it wrong. So how should I set up my percent? So my percent mass by mass is equal to, what's my solute? 10 grams KCl. What is my solution? This is what? 100 grams of distilled water is the solvent. If this is the solute, what is my mass of solution? 110. So you could do 100 plus 10, right? So you know it's where you're getting that from. So this is the water, this is the KCl. So then you get 110 grams, that should have been grams, of solution times 100. I always forget to write the 100, sorry. So be careful with that, because one of the answer choices will be 10 divided by 100. Absolutely. So you have to know what you're doing. So what do you get? I got 9.09 mass by mass KCl. Yeah, don't let that trip you up. Don't let that trip you up. Okay. How many grams of NaCl must be combined with water to prepare 500 milliliters of a 0.9% mass by volume physiological saline solution? What is physiological? What does that mean? Normal. That's what your body normally has. I am telling you that this is something that you need to memorize. That is absolutely one that you need to memorize, and there'll be another one later, but we'll talk about it when we get there. You need to know that normally, if you're going to prepare a saline solution, an IV, you need to make sure that you know what the saline concentration is for an IV. Otherwise, you are going to seriously hurt your patients. So that is one of those things you have to learn. Okay, so I'm really going for grams of NaCl, right? And I want to prepare 500 milliliters of it. So I'm going to use my percent mass by volume equation, but I'm actually given the answer in this. I have a 0.9% mass by volume. What I don't know is my grams of NaCl. But I do know my solution volume. What's my solution volume? 500 milliliters of solution. So can you solve for X? What do you get? So X is equal to 4.5 grams NaCl. Absolutely. Okay, so you'd have to combine 4.5 grams of sodium chloride with 500 milliliters of water to make a 0.9% solution. All right, so here's where we're talking about that ppm, right? The one above had parts per billion. This one has parts per million. So what is the concentration in parts per million of a solution containing 1.50 milligrams of copper and 100 milliliters of tap water? Why are we using parts per million? Like, why can't we just use percent? So you would do it, if you did percent, it would be out of 100. So it would it would be something like 0.000. It's hard to look at numbers like that. It's hard to understand numbers like that. So typically, if you're given a question like this, your answer is typically going to be between 0 and 100. If you get something that's not between 0 and 100 for a parts per something, you did the math wrong. So think about things that you don't want to have a lot of in your water. Do you want to have a lot of copper in your water? Like, that's not something I want to ingest. How about you? No, thank you. But water does run through pipes, copper pipes. So is it going to be non-existent? No, there's going to be some, but there's a threshold, right? If a pipe breaks and it starts leaching copper, that's something that the health department needs to know. And so water is tested regularly to make sure that you don't have more than you in the mail. You get it. Have you ever seen it? It's mailed to your house. As a taxpayer, it is mailed to your house. And it tells you the water quality of our area, right? If you had something that you really don't want to have in the water, then you're going to be counting it in parts per billion. So for example, fecal coliforms. You know what that is? Bacteria from your poop. You want to have a lot of that in your water? No, that's going to make you really sick. So those are some things that you count in parts per billion, right? Okay, so let's go back to the copper. So what concentration do we have in parts per million containing? So our parts per million is equal to, it's equal to, what's our formula? Grams of solute over what? Milliliters solution times what? A million. But this is grams of solute. What am I given? Milligrams. So what do I need to do? I need to convert it. So I know I have 1,000 milligrams in 1 gram. So I have how much? Move it 1, 2, 3, 0.00150 milligrams. So I'm just going to plug that into my formula. ppm is equal to 0.00150 milligrams per milliliter. And then I'm going to multiply that times 100 milliliters. A million. What do you get? Where I am on my paper. Oh, it is supposed to be grams, not milligrams. Thank you. $15. Did we get a number that's between 1 and 100? You're probably going to get a number between 1 and 100, right? Because that's why we use it that way. That's why we use it. Okay. Dilutions is another huge thing that you are going to have to do. So you have to think, if you work in a hospital, you work in a doctor's office, right? You're going to have a supply cabinet that has all the stuff that you're going to need to treat a patient, right? But if you kept everything at the concentration that you would use to treat a patient, you would have so much stuff that it would overflow your supply area. So typically what we do is we purchase things that are high concentration, that are 100x concentration. What does that mean? What does X mean? 100 times the concentration that you would normally use on a patient, right? So that you can go into the stock room, the storeroom, take a little bit out of that stock, dilute it in water or alcohol or whatever it needs to be diluted in, and then you have a working solution for your patient, right? That way you can ship it for cheap, you can store it more cheaply, right? It just makes more sense. It's easier. So are you going to have to do dilution calculations? Probably on a regular basis. Okay, so like you need to know these. There's a formula for all dilution problems. What is that formula? CFBF. Some people learned it maybe in high school as like C1 V1 equals to C2 V2, right? Something like that. But the initial is your stock. Stock is something that is high concentration. Your final is what you're going to actually give to the patient. So this is like our working solution. And the working solution is low concentration. Okay. So let's look at our example. How many liters of a half normal saline IV solution with a concentration of 0.45% mass by volume can be prepared from 1 liter of a 9% mass by volume stock? So all I do is I go and plug this into my formula. So here is my stock information, right? And then here is my working solution. And I'm asked how many liters, and that's part of my working solution, right? So this red is my stock, okay? So I'm gonna go and I'm gonna plug this into my formula. My stock is my initial. So my initial concentration is 9.0% mass by volume. Now, whenever you're doing this formula only works if if everything is in the same units. So if your concentration on one side is percent mass by volume, what does it have to be on the other? Percent mass by volume. If it's liters on one side, it's got to be liters on the other side, right? So just be careful of that. Okay, and then my volume initial was 1 liter. My Concentration final, I want at 0.45%, and it is mass by volume. And the mass by volume, percent mass by volume, it cancels out, right? And then my unknown is my volume final. So I'm going to divide by 0.45. What do I get? Yeah, I got 20 liters. And then you got to put a point there, right? Because, well, no, oh no, it would really only be one. It would really only be one, which is sort of sad, but okay. Right? So you could make 20 liters from only a 1 liter stock. That makes sense, right? We can make lots and lots of a 1x concentration, a normal concentration from our stock, which is how it normally goes. Okay. A patient order requires 1 liter of a 0.5% benzyl chloride antiseptic. You have a 12% stock solution. This is like word for word what you're going to actually have to do. How much stock solution will you need to prepare the order? What are you going to do? Going to get out your formula, right? You're going to say CIVI is equal to CFVF. So what's my initial? Remember, this side of the equation is the stock. So tell me about the stock. What's my concentration of stock? I have 12%. And if they don't have weight by volume, volume by volume, just assume that it's the same unless it's given and it's different. So you can just assume it's the same. All right, what's my volume initial? That's my unknown. That's what I want to know. Okay, concentration final, 0.5%. Okay, volume final, 1 liter. So I'm going to divide by 12. Volume initial is what do you get? 0.04. Give me one more sig fig. 2. I know it only requires 1. But now, are you going to the stock room? Do you have a device that measures 0.042 liters? That makes no sense whatsoever, right? It's a correct answer, but it makes no sense. So let's say you're really there. What are you going to do? You're going to convert it to milliliters because you can now measure milliliters. So how would you do this? Because this is something you're actually really going to have to do, right? You're going to multiply by what? So I know that I have 1,000 milliliters in 1 liter. So my liters will cancel and I'll end up with 42 milliliters. Can you measure out 42 milliliters? Absolutely. Absolutely. Now, would you add 42 milliliters to 1 liter of water? Why not? What do you mean? Like if I want to make this, I have this patient order and I know I need 42 milliliters of this antiseptic and I have to add it. Let's just say it's diluted in water. Do I add 1 liter of water? Because that's my final volume. Do I add a liter of water? I have to subtract, right? If I added a liter of water and 42, I would have 1 liter and 42 milliliters at the end. So how much water would I add? How much water would I add? I want to get to a final volume of 1 liter, which is the same thing as 1,000 milliliters final. So how much water do I add? 900. 58 milliliters. So be careful with that, right? Sometimes you have something big that'll measure a liter, and like you pour your 42 milliliters in and then you just fill it to the line and that fills it to a liter. But sometimes you don't have that. So just be careful, because if you did it to where you did 42 milliliters plus a liter, you would have not a 0.5% solution. Maybe you would have a 0.48% solution. And maybe that's not strong enough, right? So you have to be very careful about that. Okay. Oh. Was 42. This. Just because I know that you're practically going to be doing this. You're actually going to be doing this. You know, I want you to understand how it really works. Like, we could solve the problem and just get the answer. But then when you get to actually doing it, you're going to be like, okay, I got 42. I did the math. Dr. B didn't tell me what to do next, right? So how would you actually make it to bring to the patient? That's what you would do. Yeah. Okay. How would you prepare 2 liters of a 1 molar magnesium chloride from a 5 molar magnesium chloride stock solution? You might need 2 liters of a 1 molar solution for something. So we're going to use our same formula, CIVI, CFVF. So here is my stock solution, and this is my working solution. So my concentration initial is what? 5 molar. What's my volume initial? Unknown. Concentration final? 1 molar. Volume final? 2 liters. So we divide by 5. Volume initial is? But are you going to measure out 0.4 liters? No, what are you going to do? You're going to convert. You're going to say, I know I have 1,000 milliliters in 1 liter, and so I'm going to need 400 milliliters. Am I done? Nope, because I'm trying to make a solution, right? I'm trying to make a solution that is 2 liters. 2 liters is the same thing as 2,000 milliliters final, right? I'm adding 400 milliliters of MgCl2. So how many milliliters of water do I add? 1,600. So do you see how before just 42 mils doesn't seem like that much? But like, would this make a difference? Holy crap, yes. This would make a big difference, right? So you always want to keep that in mind. So y'all see where all those numbers come from? Yeah? Okay. Today is a very practical day. Very practical day. All right. You must prepare 400 milliliters of a disinfectant that requires a 1 to 8 dilution of stock solution. How much of the stock solution will be required? Now, before we talk about this, I want to talk about Campbell's chicken noodle soup. Right? I'm crazy. So Campbell's chicken noodle soup, what do you do with the soup? Y'all know the condensed soup? Okay, so in the grocery store, you know where they have all those cans of like cream of mushroom soup, cream of celery soup, cream of you know, all this kind of stuff. Have you ever opened one up? It's like super thick, right? If you ever make for Thanksgiving, you make green bean casserole, and you make it with the cream of mushroom soup, right? Yeah. Yeah. Okay. So it's really, really thick. So if you were going to make soup with it, what you would do is you would take the can, right? So you have 1 can of whatever it is, and you pour that into the pot, right? But it's thick. So what do the instructions tell you to do on the back? Fill up the can with water. So you do 1 can of water, So you do soup 1 can of water, and you put both into the pot, and that makes your soup, right? So the soup can, what do you do to make it into the pot? What kind of a dilution is that? Everybody wants to say that. Everybody wants to say that. But when you look at a dilution, you see the up here where it says a 1 to 8 dilution? The first number is the part. The second number is the whole. So if I did this, the soup can dilution, I would do 1 can, right, to my whole. What's the whole? 2. So that's a 1 to 2 dilution. This is another place where a lot of people have problems, but you have to, if you remember that this second number is the whole and not most of the parts, right? It's going to make sense. Okay, so now let's try to go up. Now that we understand what a dilution is, right? Let's say I wanted to do, let's do another one. I want to do a 1 to 5 dilution. That would be like 1 milliliter of my drug plus what? 4 milliliters of water to equal a total of 5 milliliters of my working solution. So I would do a 1 to 5 dilution, right? This is a 1 to 5 dilution. Be careful with that, right? Because basically what you're saying is I want a 1x concentration and I started at a 5x concentration, right? That's what those are saying. So up here, I have to prepare 400 milliliters of a disinfectant that requires a 1 to 8 dilution of stock solution. Look at your equations. Look at your equations. I'm holding up the wrong sheet of paper. The dilution equation. Do you see the very last one? Dilution factor is equal to volume final divided by volume initial. So if I want to do that, right, dilution factor is equal to volume final over volume initial. I don't know my volume initial, right? That's unknown. But I know my dilution factor. What's my dilution factor? So 1 to 8, so we call it 8. So 8 is equal to my volume final, which is 400, over my volume initial. Can you solve for volume initial? Cross multiply, right? So you get volume initial is equal to 400 divided by 8. What do I get? 50. But now that you have your answer, right? How much of the stock solution is required? This is 50 milliliters. Oh, I can't move that. This is 50 milliliters of stock. How many milliliters of water do I add to get to a final volume of 400 milliliters? 350. If you're making something that's a disinfectant, if you dilute it wrong, it's no longer a disinfectant. And that can be a really big problem. No, I got it right here. You just take, it's always going to be 1. A dilution, it's a good question. A dilution is always going to be 1 in something, right? So that 1 is like basically understood. So the dilution factor is the 8.
You just take the whole.
Yeah, you just take the whole. Yeah. Practice these. And if you have problems, please send me an email and please ask me. Okay. All right. So now, osmosis and diffusion. Love osmosis and diffusion. So what's the difference between osmosis and diffusion? Osmosis is movement of water. Diffusion is movement of anything else, right? So remember we talked about this with the red blood cells? right? Y'all remember this? So I had two situations. I had my red blood cell and I had my red blood cell, right? And so in one situation, right, I have the same number of particles, 1, 2, 3, 4, 5, 6, right? So in one situation, I only have a few particles outside of the cell. And then my other situation, I have tons, right? Yes. So in the first situation, what is going to happen to that red blood cell? Water is going to do one of two things. The particles, we're going to assume the particles can't move. They're either too big, they're charged, they don't want to go through the membrane, whatever it is, they can't move. What is water going to do? Osmosis. Is it going to go into the cell or out of the cell? It's going to go into the cell. Why is it going to go into the cell? To dilute the concentration of stuff inside the cell so it matches the outside, right? So the cell will what? Will swell and possibly burst, right? Okay, how about my second situation? What's water going to do? Water is going to go out of the cell. H2O is out. So this is water in, this is water out of the cell. What's going to happen to the cell? It is going to shrivel. Shrivel. So the other word for shrivel is crenate, right? Scientific. So this is pretty easy to understand, right? But the question is, you will be asked this, what kind of a solution is cell, we'll call this cell number 1 and cell number 2. What kind of a solution is cell number 2 in? Hypertonic or hypotonic? Hypertonic. But how do you know this? This is the way I remember. I did this in the video. So when I think of hypertonic, I'm a cat person, although I only have a dog right now, but I'm a cat person. So I think of a little cat, right? It's a little cute cat. And I always draw a fat cat. I don't know how to draw a skinny cat, right? His little paws, right? He's got a little nose and he's got whiskers, and I'm a terrible artist. But he purrs, right? And the purr comes out of the cat, right? So it's like water. Water is leaving the cell, so it's leaving, so it's hypertonic, okay? Now, in situation 1, what is the solution? This is hypotonic. Why? How do you remember hypotonic? Well, when I go to cook, right, what do I put in my pot? I put water in. I put water in my pot. Hypotonic, look at what it has inside of it. The word what? Pot, right? Water goes into the pot. Hypotonic. So if you have trouble remembering hypertonic and hypotonic, that's how I remember them. You know. Okay, so now let's apply this. We have a lettuce leaf in the produce aisle at the grocery store, and it's accidentally, oh my gosh, yes, go ahead. No, we're going to keep going, and we'll pick up, we'll finish 8 on Tuesday, and then we'll pick up on 9. So we're just going to keep rolling. So we have this lettuce leaf and it's accidentally submerged in water. So what happens to that lettuce leaf? Are you putting it into a solution that has lots of stuff in it or not so much stuff? It's plain old water. Did we put a lot of, is it salt water? No. So it doesn't have a whole lot of stuff inside of it. So what's going to happen to the cells of that lettuce leaf? You don't have so many particles outside, so it kind of looks like cell number 1, right? So what's going to happen? Water is going to enter the cell. Water is going to enter the cell. Now, if water enters the cell, what is going to happen to those cells? Are they going to swell or are they going to shrivel up and crenate? They're going to swell. They're going to get big. So now the question is tap water hypertonic or hypotonic to our lettuce leaf? So if water is entering the cell, what does water do? It goes into the pot, so it is hypotonic because we have the pot there, right? Okay. All right. So I know lettuce leaf at the grocery store doesn't sound that important, right? It really doesn't. But it's a good illustration of the point. So why is this important in medicine? Inside of your bodies, right, you have two kidneys. What is the job of your kidneys? Filter your blood. They are your filter unit. So you have lots of waste products that are made by your cells every second of every day. And what happens is that your kidneys will filter that waste product out and put it into your urine so you can excrete it and be done with it, right? But what happens to patients who undergo kidney failure? They go on dialysis. There are a couple of different kinds of dialysis, but dialysis is quite simply put a big machine that acts like your kidneys, but is outside of your body. So in hemodialysis, hemo meaning blood, they take a tube, right? And it's like you're giving blood, but they take your blood out and the blood goes through this machine. Now, inside this big machine, you're going to have blood, you're going to have a permeable membrane, and then you're going to have what's called dialysate, or the liquid that's in the machine, right? So what do you want to happen in a dialysis machine? If it's supposed to take the place of your kidney, we want the waste particles to go into the dialysate, right? But at the same time, there are certain concentrations of things that have to be the same, right? So particular ion concentrations, things like that. If I take everything out of the patient's blood and then put it back in, it's not going to be good, right? So you have to have a certain concentration inside of what's called the dialysate. So you're going to pull the blood out, and the waste is going to move towards the dialysate until it equilibrates with the dialysate, right? So when it goes back into the patient's body, now it's the same concentration that that dialysate was after the exchange happened, right? Okay, so if we have a patient that's undergoing hemodialysis, the blood is going to leave the patient. It has a higher, lower, or the same osmotic pressure. What causes osmotic pressure is number of particles inside the liquid. So when the blood leaves the patient, how many particles do you actually have? A lot or a little? A lot. It's filled with waste, right? It's lots of waste. So as the blood is leaving the patient, you have lots of, oh, I'm on the wrong one, aren't I? Leaves the patient. We have lots of waste. So the more stuff you have, the higher pressure you're going to have. So tell me, what's the osmotic pressure compared to the dialyzing solution? It has more or less than the dialyzing solution? It has more. So it's going to have a higher pressure, right? Then you're going to have a chance for that equilibration to happen, for things to move from one side of the membrane to the other, and all your waste particles are going to move over. So then the blood is going to re-enter the patient. Now, the osmotic pressure is what compared to the dialyzing solution? The same. Why is it the same? Because it equilibrated, right? That's the definition of equilibrate. Is that once that equilibration happens, that you have the same concentration on this side as you do on that side. So you have equilibrated. So now what is your osmotic pressure? Is the same as the dialyzing solution, right? Okay. So do you remember when I said you had to memorize some physiological conditions? There's some that you just have to know. One of them was what? 0.90% what? Mass by volume, NaCl. That's one of them, right? You have another one that is glucose. So you have typically 5% mass by volume glucose. And glucose is abbreviated D5W because it's D-glucose, right? Remember we talked about that? D and L, it's always going to be D-glucose. So this is what's going on in your blood at all times, right? So if you give a patient an IV of something and you don't want their cells to change, what do you give them? Something that has 0.9% NaCl and 5% glucose. So this you have to know. No, memorize. Okay. So if I give a patient, look at 8.52, if I give a patient 10% NaCl, what's going to happen to that patient's blood cells? Is that like my hypertonic or my hypotonic solution? Compare it. I have 10% here, and inside the cell I have 0.9. This is way higher, right? So this is a higher than the cells. So what's water going to do? Water is going to leave the cells. So then will the red blood cell undergo crenation, lysis, or no change? Not no change. Do I hear no change? Well, what is, okay, so what is crenation? Shrivel. So crenation. Shrivel. Okay. Distilled water. Distilled water is like saying I have 0% NaCl. Distilled water is no ions. So if I have 0% compared to 0.9, I have more or less than cells. I have less than cells. What's water going to do? Goes into cells. What's the cell going to do? It's going to swell, and they didn't give you swelling as a choice. They gave you lysis. I don't know if it would really lyse, but it would swell, right? It would swell and possibly lyse, undergo lysis. Okay, 5% NaCl. Higher, lower, or the same? Higher than the cells. Water is going to do what? Water is going to leave. A, B, E. What's going to happen? Shrivel and crenation. Okay, last one. Glucose, 5%. It's the same. So it's going to be no change. That's awesome. So what I'm going to do is I'm going to go in and I'll update the calendar, right? So for next time, we're going to finish 8 and we'll start 9. And I'll update the 1. So at least through section 2 of chapter 9. Okay. Y'all have a great weekend. See you next time. Anybody on Zoom and anything?